So on Monday, I'm talking about the isotope. So let's recall it. What are isotopes? So isotopes are atoms of the same elements that have the same number of protons. Most elements occur naturally with a varying numbers of neutrons. So atoms of the same element that have a different number of neutrons in the nucleus, they are called isotopes. So isotopes have the same atomic numbers, which is the same numbers of protons, but it has different mass number or different number of neutrons. Earlier of this chapter, I'm talking about Dalton model, and in Dalton model, it states that all atoms of an element are identical and have the same properties. So now you learn about isotope, you realize that all atoms of an element, they don't have to be identical, because isotope, they are not identical. They have different number of neutrons. So that's why I told you that later on, these things that listed on Dalton model was proven that it's not correct. So let's look at iron isotopes. Iron had three different isotopes: iron 56, iron 58, and iron 59. Now for iron 56 isotope, it has 30 neutrons. Iron 58 isotope had 32 neutrons, and then iron 59 had 33 neutrons. So you see, iron isotopes have different numbers of neutrons. How you determine number of neutrons? You can calculate from the mass number, because the mass number is defined by the sum of protons and neutrons in the nucleus. You can find the mass number on the atomic notation. Sometimes it's given to you in the question. So we talk about atomic notation on Monday. On the atomic notation, the top left, it shows you the mass number. The bottom left, it shows you the atomic numbers. For example, the atomic notation of carbon 13. So for this carbon isotope, it had a mass number of 13. It had an atomic number of 6. Now let me set up here, because the mass number, the sum of number of protons and number of neutrons, you can count the number of neutrons, which is the difference between the mass number and the atomic number. So for this carbon isotope, it has 7 neutrons, because 13 minus 6 equals 7. So make sure you know where to find the atomic numbers or number of protons is when the information is given to you. Now for the period table, you can see that it's on the top left of the element symbols on the period table. For example, for fluorine, the atomic number is 9. It had 9 protons. For uranium, the atomic number 92. It had 92 protons. Nitrogen atomic number 7. It has 7 protons. Now, there's another numbers that appear on the period table under the name of the element. This number is not a mass number, it's atomic mass. So for fluorine, the atomic mass is 18.998. For uranium at 238.029. This is atomic mass of uranium, not the mass number. Same thing for nitrogen, 14.007. This is the atomic mass of nitrogen, it's not the mass number. So you see, like I said, on the period table, the atomic numbers is on the top left, but it is on the bottom left on the atomic notation. So you make sure that you know that where to find the atomic number depend on what is given to you. If it's given to you at atomic notation, it is at the bottom left. Okay, for the on the period table, the number under the name of the element is its atomic mass. Now on the atomic notation, the mass number is on the top left, like I said in the previous slide. So you want to ask yourself, what is the difference between the mass number and the atomic mass? So the mass number, like I said earlier, is the sum of protons and neutrons in the nucleus. Atomic mass is different, and the atomic mass, on the other hand, is the weighted average mass of all isotopes. So before we talk about weighted average, we must to distinguish between the simple average and the weighted average. So the simple average assumes the same number of each object. The weighted average takes into account the fact that we do not have equal numbers of all objects. So the weighted average is calculated by multiplying the percentage of the object at the decimal numbers and by its mass for each object, and then you add all the numbers together. Let's look at example. Assuming I have a bag of 10 beans, purple, pink, and white. So for the purple, each of the purple beans had a mass of 11.0 gram. For the pink, it's 12.0 gram, and for the white, the mass is 13.0 gram. Now, for the average, the simple average mass, it assumes that the pink, the purple, the number of beans of purple equal the number of beans of pink, number equal to number of beans of white. So the simple average mass, you just take the mass of each type of beans, add together, and divide by three color types. So you divide by 3, that gives you the simple average mass of the beans is 12.0 gram. Now, because its bean color, the numbers of its bean colors is not the same, it's different. For example, here for the purple, I had 3 beans. For the pink, I have 5 beans. And for the white, I have 2 beans. So you're not going to use the simple average mass. It's not accurate. So you have to calculate the weighted average mass. How to calculate it? Remember, we talked about earlier that you have to take the mass of individual or each object multiplied by the fraction. So for the purple, the fraction is 3/10, right? Because you have 3 purple over total of 10 beans. So the fraction 3/10. For the pink one, it's 5/10. And for the white one, it's 2/10. You take each fraction multiplied by the mass of each type of bean, each color, and you add them together. That gives you the weighted average mass. Now let's take an example for carbon, calculating the atomic mass of carbon. So carbon have more than 2 isotopes, but only use 2 isotopes here at the example because these are significant. Others isotopes, only real small trace can be found. So carbon-12 isotope, the relative abundance or percentage is 0.989 or 98.9%. For carbon-13 isotope, the relative abundance is 1.11% or 0.011. So to calculate the weighted average mass of carbon, first you take the mass of carbon-12 isotope, which is 12, you multiply by the relative abundance or the fraction or the percentage, and then you add with the second isotope here, the carbon-13 isotope, the mass is 13, and then the relative abundance is 1.11% or 0.011. So when you add them together, it gives you the weighted average mass of carbon. If you look at the 12.011 that we calculated here and compare to what you see on the periodic table. So on the carbon, you can see the atomic mass of carbon on the periodic table is 12.011 because what you see on the periodic table, the atomic mass of all of the elements on the periodic table, it calculated based on the weighted average mass of that element. So it takes into account all the isotopes that naturally occur. So just remind you, sometimes you see that in the question talk about, I use relative abundance. Sometimes in the question or in assignment, it say fraction or percentage, they are all the same. So because not all isotopes and an atom are present in equal proportion, we must use the weighted average. So take another example with gallium. Gallium had 2 isotopes. So gallium-69 and gallium-71. So gallium-69 have a mass of 68.926 atomic mass unit with 60.11% abundance. Gallium-71 have a mass of 70.925 atomic mass unit with 39.89% abundance. So therefore, the average atomic mass or the weighted average mass atomic mass of gallium is you take the first mass multiplied by the relative abundance, the second mass or the mass of second isotope multiplied by the relative abundance, it gives you the atomic mass of gallium. So just recall that you can use the periodic table to obtain the atomic numbers and the atomic mass of an element. Remember, I said that the atomic number is on the top, sometimes the center, sometimes on the top left. The atomic mass is at the bottom and usually under the name of the elements. So the periodic table shows the atomic number, the symbol, and the atomic mass of the element. We will do some of the practice in class. So these are some of the example we will do in class when I see you in class.